doesn't matter what n is, but there is one condition about p. What is that? P is prime number and odd prime number, right? Yeah, it's odd prime number. That was the theorem, and we're trying to prove the case when n equals 1 yesterday, or last time, and it was stopped. Okay? So let's review and all the other things. And then there is this, now in that n equals 1 case, the z mod p is denoted by what notation? Different notation, right? Fp, finite field. That's the same thing. It's a special property, so we use this Fp. So with this coefficient over finite field, everything is divisible and has multiplicative inverse except 0. Because of that, we have unique factorization theorem. What is factored here? Fp doesn't have an integer notation. Everything has multiplicative inverse. There's no notion of integer. But what unique factorization were we talking about with this finite field? What is uniquely factored? Uniquely factored into irreducibles, right? You can't split any further. What is factored? Polynomials. Is this yeah, polynomials. Not just the polynomials, but polynomials with coefficient from where? Over this finite field, right? Remember z mod 6, what happened z mod 6? Anybody remember that? You did the homework? It factors different, right? Yeah. So doesn't work, but Fp works. Unique factorization is important. And there was also factor theorem. What was factor theorem? If you have a 0, right? It translates to what? A factor, right? What was the factor? X minus a. Something like that, x minus a. And then we also talked about something that we hesitated to actually conclude. And this works for what kind of coefficient? Over finite field, right? More than that. More than that. Anything works. Anything. Doesn't matter. Because of what property of the divisor? It was a monic property, because the leading coefficient of 1, you can match anything, right? But if the coefficient is a 2x minus 1, then if you're in z mod 6, then you can't multiply something 2x to knock down each of the term. 2 is not multiplicative, have the multiplicative inverse, right? So if I'm looking at 5x, the fifth down there, underneath the dividend, there's nothing to multiply 2x to match that 5 times x to the fifth. Think about long division, right? Doesn't work. 2, you can't get 5. That make sense? Yeah. So if you think about long division process, if that's your divisor, you cannot always knock down one term because 2 is not invertible. But here's a monic. So coefficient is 1. You can match anything, right? So that's why the monic property allows us to do that over any coefficient ring. But what is it we don't have? We can divide. We have a factor in there. But uniqueness is not there, right? Remember? Uniquely. Next time when you try to factor, maybe this guy disappeared. Because of z mod 6, I have x minus 2. And the other guy factored it. He didn't have x minus 2. Something else appeared, right? So uniqueness disappears. But if we have finite field over there, of course, once you have it, whoever did it, it appears in one way or another. Make sense? That was factor theorem. And there was a subtlety in the coefficient part. We use that. And the most important thing about this lemma that some of you prove it recently. What is this lemma over the finite field? So we assume a finite field, this is a special case that I had to write it down. It's a counting lemma. It's about this set. A coming from, the star is not necessary, but I'm emphasizing coming from invertible elements. A to the n equals 1, where n is fixed, right? Such as 2. You know, how many elements are there in this here? At most n, that is correct. It has at most n. Not always n. At most n elements. For example, F2. F2 has 2 elements. F2 star has 1 element. So a squared equals 1 has only one solution, right? A squared equals 1 over sigma 2 squared, no, F2 star. F2 star has how many elements? 1. So 1 works and that's it, right? Doesn't have 2 elements. It's 1 element. And by choosing this wisely, according to the order of this element, you can actually create lots of examples that this one has only 1 element in there. But if it had some common factor with the order of A, then you can see that it picks up more elements. But what we're going to use here is at most an element. It doesn't exceed. You did some homework problem where A squared equals 1 over some z mod m. You counted there are 4 elements, things like that, right? So this is important in part. And using that, there was a corollary. Who remembers about the immediate corollary that we were using when you're computing the manipulating the order, isn't there? It goes like this. If the order of some element g is n, then what do we know about this relationship between g and that? Now what's it, right? The bracket g is equal to what? All these elements in here is the powers of g, right? And g to the n here is 1. That's what you're saying here. So do you think that g is an element of this set here? A to the n equals 1? Is g just one element itself? Let me write down here, over here. Is this g is this element of this set? Anything raised to n equals 1. G is an element there, right? Order is n. How about all the other things? G to the power, g to the third and all that thing. Do you think it's there too? If you raise any of this type, do you get 1? Well, if you swap this, right, g to the n is 1 raised to k. So every element in here, right, is inside that set. Is that right? Yeah. If you raise anything in here, raised to n, it becomes 1. So that's contained in this set. But what makes it equal to each other? Remember this? We just argued that any power is here. If you raise to nth power, it becomes 1, right? But why is these two things exactly equal? It's a corollary, right? So why is it a corollary? Means you use this lemma to conclude this. How does the argument go? How many elements are here? N elements. And how many elements are there? At most n. What could happen? It must be equal, right? That was the argument from last time. Make sense? All right. So that's that. Let's review. And something that you proved today, I guess, lemma. It's very useful actually computationally, and here it's going to be a very important thing to have today. Order A and order H has order B, right? What is the additional condition to have definite result?
A and B are relatively prime.
Right, A and B are relatively prime. If you have that condition, then we can conclude order of product, right, is A times B, right? Remember you did the homework? I hope you found some examples that there's no easy formula if you don't have this condition, A and B are relatively prime. Remember there's some homework problem asking you, find examples, and maybe it's LCM. And then you realize that in this case, LCM is the answer. In this case, LCM is not the answer. Something like that, right? So this is an important thing, but it seems like a huge limitation, but actually it's not. It's you can control this condition very nicely. All right. So that's how much we have so far, and then you understood the proof. What is the main tool of the proof of this lemma we just stated? Maybe you would have, there are multiple different proofs here, and none of them are particularly effective. I just try to stick to the order formula. I just like that formula. Try to do everything with the order formula, and you will see even today we finalize the whole thing with the order formula. So I use the particular order formula, but there are other proofs that are as effective as that one. All right. Those are I'm showing here is the main picture right now. This is our goal right there. And we have this nice unique factorization that is something you're used to. And fundamental theorem algebra over rational number, you expect this thing too. A to the n equals 1. You don't expect more than n solution to x to the n equals 1 in even real numbers. And some special thing about this order of n being inside and here. All right. Then we began the proof, actually, to the proof of the case that Fp star is generated by one element, if P is odd, right? We began that, okay? So what was the method of this one? Proof by contradiction. That's how we started here. So it's a proof by contradiction. Let's write that down. You just remember, ineffective because of this. Proof by contradiction. It really tells you nothing. Then you made what you have supposed is wrong. So what will be the statement? Suppose we have G, right? G has order. Did I use n? I use n, right? And has a maximal order, right? That's what we said. Has maximal order. N. How do you understand this maximal order? If I give you G, it has an order, right? What do I mean by maximal order? You go through all the elements in Fp star, and you find the one with the largest order. That's what I mean by that. All right? Maximal order. All right, again, there's this Fp star. There are a lot of elements in there. Find one element that has largest order, okay? And if that's p minus 1, we're done. That's not by contradiction. We're saying the largest order is even less than p minus 1. That seems like negation of the one we're to prove, right? Right. We have this element G as maximal order, and which is less than p minus 1. If this is necessarily arriving to a contradiction, we prove that, okay, maximal order must be p minus 1. Therefore, there has one element that reaches that. Do you have a question? Yes.
So in some contexts, maximum.
Right. I think a maximum is usually referring to a value. So because maximal order is a number, maximum order is a better way to choose it. But sometimes it's a partially ordered. It's not like totally ordered. Therefore, if there's a maximum, there's a unique maximum. If it's a partially ordered, therefore, like a containment of sets. And usually they use this term a maximal property or something like that. So I have a tendency to use the maximal rather than maximum. But if you're in analysis or things like that, they tend to use the term maximum. In algebra, they tend to use maximal. And even they use an indefinite article, a maximal. even in the context that the maximum is unique. So you should have actually used the maximum, but they have a tendency to still use the a maximum because it doesn't matter that it is unique or not. What it matters is that there is a maximum, something like that. So that's how I figured it out. I never asked this one particular to anybody in my education, so that's how I figured it out. But I hope this is all right. But anyway, this is a maximum order, and it is less than p minus 1. This is something's going to go wrong, right? All right. Then there is this h. Remember h? Right? Because this is less than p minus 1, then there is, then what? Then there is h. H is in outside of something, right? What was that? It was not in that bracket G. How many elements are there in the bracket G? We don't know, but definitely less than p minus 1, right? Because the order is less than p minus 1, this cannot have p minus 1 elements. So there's something out there. This guy has a p minus 1 elements, right? So there will be something out there. It's not in this one, right? So existence is clear. This one doesn't have p minus 1 element, so there will be something out there. P minus 1. Good? But we didn't just grab anything. Always grab a good thing, right? So we're going to grab h with minimal order. Is that right? Minimal order? Minimal order. What did I call that? M, right? All right, M. So don't just choose anything. If you can choose a good one. Smallest one, largest one, something that was divisible by whatever, that reduces your argument a lot. If you don't do that, sometimes you have to kind of, a lot of dissent and clearing up process, the argument gets longer. So that's the situation, right? Okay, so then there's this M and N, okay? And some relationship. Anybody remember the relationship? That was an important statement here. I think that was a homework problem, right? It was a homework problem. Let's do that. Anybody remember the relationship between M and N? I think the key thing is this corollary. I'm going to color this corollary here. I think this is something that we use for that statement. So what about M and N? What is the relationship? M doesn't divide N. Thank you. Wasn't that the homework problem? You proving it? Yeah. So let's recall the process. So why does M does not divide N? Suppose it does, right? If M divides N, here's a little proof. Oh, proof. That's what I meant. Proof here of that statement. If M divides N, what was the consequence? M divides N. Where's N? N appeared here. Order of G, and I was pointing to some condition in here, right? So if M divides N, then h to the m is what? What do you know about this one? What's h to the m?
1.
It's 1 because?
That's the order.
That's the order. So right to the end. Well, then what's the next step? And m is dividing n. So can you change to a different power? H to the m is 1, and m is dividing n, and h to the what is 1? Remember that part? N, right? N. Let's think about that. Why? Maybe you can write down, okay, n is m times b, maybe? Is that right? I use b something else for something else. What can I do? K. Do we use k here? I don't think I use k. So n is m times k. So if you does that make sense? If you write this one, m times k, then it's 1. All right? M dividing n implies that h to the n equals 1. H to the n equals 1. So what was the next part? If h to the n equals 1, then h is in where? Look at this one here. What's the color here? Purple? Yeah. H to the n equals 1. H to the n equals 1. Isn't that the element of that set? Right? So a to the n equals 1. Is that right? And that is what set? Bracket G, right? But what's wrong with that? H is in bracket G, but we chose H outside the bracket G, right? So it can't happen. If m divides n, implies H is in contained G, right? Did I use the at most condition, at most n condition here? Or am I just using m is dividing n condition? What do you think? This corollary relies on that count n. So we actually use it. The fact that H belongs to this set here does not use at most n condition. But these two things being equal to each other uses at most n condition, right? So we're using that. All right. So we have the conclusion, m is not dividing n. So we use this minimal condition here, right? To pull out m is what? In what form? Prime power, right? M is a prime power. The minimal, let me write down like this. The minimality implies what? M is in what shape? Right, P to the A, but P was used for something else here, so I'm going to use Q to the A, right? That was the conclusion. It wasn't that short argument. Let's go for it. So what was that? Minimality and m does not divide n. I think we should, these two things together imply that, right? So I'm going to put this brace in here and think about the proof of this guy here. How did that proof go? First, we write down m equals in what form? Prime power q to the a, right? And some part that is relatively prime to q. You can always write that, right? So what did I write? Is that a t? I forgot what I used. M prime? M prime is what I use, right? M prime. You can always write, we don't know what q is. Q is just an arbitrary choice here, right? But there's going to be a q special choice such that what condition do we have? Q to the a, and this time we're using m does not divide n. We have always prime factorization, m into powers, the product of powers of primes. Which q are we going to choose from this condition q, m does not divide n, right? This is the prime power that does not divide n. How do you know there's such a prime divisor? Can somebody answer that? You write down m as a product of prime powers. How do you know there is at least one prime power that does not divide n? Right. If there's no such prime power, m will divide n. If m doesn't divide n, means there is at least one prime power that doesn't divide n. Does that make sense? It's a distinct prime power, relative prime condition is very key here to conclude that. All right? Unique factorization of integers is used here. Make sense? All right, this consequence uses what? M doesn't divide n, right? What does minimality do here? Minimality implies m prime must be 1, right? That's what it is. So here, let's, what do we do? Order, then we calculate order of which element? H to the what power? M prime, right? M prime. Then what is the order of this one? Order formula. What is the order of H? M divided by GCD of M and M prime, right? But M prime is actually a factor, so isn't that is M divided by M prime? Is that correct? Yeah. So what is M divided by M prime? Here, m is q to the a m prime, so if you get rid of that, isn't that just a q to the a? Right? So H is the element of a minimal order that is outside G, right? So we're going to conclude this Hm prime is outside G. How do you conclude that? H is outside G, right? Why is Hm prime is outside G? Hm prime has this order, right? Does this order divide n or not? Doesn't divide n. Let's see. Go back to this guy again. If something is in this element here, if you raise to the n, it becomes 1, right? If it is inside this G bracket, you raise to the n. Anything raised to the n equals 1 means order is dividing n, right? So here, q to the a dividing n implies h to the m prime is in the bracket G. Can somebody explain this? If q to the a divides n, then Hm prime is inside that bracket G. Why is that?
Because since n is a multiple of q to the a, then that means that q to the n is equal to 1, which is an element of G.
Right. This one has order q to the a, and it's dividing n, so must be this element of this q to the n divides it. Q to the a is here, part of this n. So that's why, because this was h has this property. If you raise this one, m prime, to the nth power, it becomes 1, right? Because n has this q to the a in it. And q to the a together with m prime is the order. This one has this order q to the a in it. So this is one. What am I saying? So, no, I think I argued it backwards to conclude. It is not wrong, but what I want is that if h to the m prime is inside this G, then can we conclude that q to the a divides n? That's easier to argue, right? Is this backward easy? If h to the m prime that we're just considering here with the smaller order is inside this G, then in this element, and this order divides n, right? Is that correct? Yeah, that's easier to see. So what is the contrapositive statement of this? If this doesn't happen, then if this doesn't happen, and this one doesn't happen, right? So if q to the a doesn't divide n, which is the fact we have, and you're flipping the side, and you conclude that h to the m prime is not part of this element in there. Is that right? Okay. Is that clear? So the q to the a not dividing n implies that our new element Hm prime is now outside the G. Okay? So because of the minimality property, so we have m is the smallest number, right? Smallest the minimal order, and we have this new element which is outside that. So m is less than equal to q to the a. Q to the a is the order of h to the m prime. And that's the order, and then that m is the minimal order, so m must be smaller. Right? But what's m? Q to the a times m prime, right? So that together implies that q to the a cancels. M prime is less than or equal to 1. So what's m prime? M prime is 1, right? So I want you to look at this one like this. Does the minimality is used to conclude that m prime? Right, here's the minimality. Used it here. This is the minimality condition there. All right, summary. If we choose this element outside G, choose one with a minimal order m, the fact that it's outside G implies that M is not dividing N. And from that, we can write this M. That's why we were doing this part. Write this M as Q to the A times M prime. That's M not dividing N part. And this M prime becomes just 1 using this minimality part. Okay? All right. So that was a review with some details filled in, and then you try to write your own proof in your own terms in the homework. All right. So summary. H is outside G, and order of H is what? Q to the A, right? That does not divide the order of G. That's the conclusion here. Good? Now it's time to, with this G and H given like this, we're going to construct an element. It's not rush. An element of order greater than what number? Let's go back. What is the statement beginning of this proof by contradiction? What was it? Suppose G has maximal order n, right? That is less than p minus 1. And if I construct an element with order greater than n, that's a problem, right? So that's what we're about to do now. Good? Greater than n. Make sense? And that'll be a contradiction. So creating an element over some sums of order is controlled by this lemma that you proved as here. Where is it? It's gone? I think I wrote down somewhere. Order A times, I remember I wrote here, lemma right there. Okay? Order A and order B, relatively prime, and you can make an element with the product of those two, right? Order. Make sense? Good. So let's write it like this. Write order of G. How do you want to write order of G? All we know is n, right? You want to compare this one with order of H there. Order of H is very clean, right? Q to the A. Is that right? Q to the A. So how would you write this n compared to that? Maybe Q to the B? Is that all right? Maybe there is no Q at all. Then in that case, B is going to be 0. And all the relatively prime part is going to be T. Is that all right? There's a Q appeared in the order of H. Then write this order of G as a prime power of Q and relatively prime power. And I want you to compare this size of A and B there. Who can do that? The fact is that Q to the A does not divide n. That's a fact, right? There's a Q to the B in prime power factorization of n. What do you know about the inequality between A and B? Doesn't divide n. Which one's bigger? B is bigger, right? If B is bigger, then Q to the A is smaller. So like Q to the first and Q to the second. So Q to the first divides Q to the second, right? So that's not quite right. So which one's bigger? Think about this one, Q to the second example. If this guy's bigger, Q to the fourth, like that, right? Which one divides what? This guy divides n, right? That's not good. It should be opposite, right? So what's bigger? A is bigger than B such that Q to the A does not divide Q to the B. That's the condition we have. Good? All right, went through examples. Now, we want to cook up an element using that lemma, right? But they have this common factor here. Don't they have a common factor? Order G has Q to the something, and this B can be possibly 0, so that's what I'm putting here, like this. Maybe there's no Q at all. Now, this order of G and order of H has a common factor, potentially common factor, Q to the A and Q to the B, right? Therefore, we cannot use that lemma, multiplying. So how are we going to get rid of this Q to the B? It's order formula. Can you think of some powers of G such that its order is get rid of that Q to the B and only has T in there? I want some volunteer. Raise G to appropriate power. So order of that G to the power is just simply T. It gets rid of this Q to the P. So let me write down that formula, right? What is the formula, order formula? Order of G, right? What's the order of G? N, right? N is now written as like this. And GCD of that plus that K there, right? Usually. That's the order formula. So I want you to go ahead and find this number, plug it in there, and after you divide it, it just becomes T. If you look at the numerator, you know what to knock down, right? Q to the B is gone. So you have to make the denominator Q to the B. What could that be? B? What should I put in here? The denominator turns out Q to the B so that it cancels Q to the B and it just gives you T. Q to the B, right? Yeah, just put Q to the B there. There it is, Q to the B. Okay? So again, we accomplished this order being T, right? Why did I do that? To use the formula. What formula? That formula right there, lemma, right? What does that require? Relatively prime of the order. So here, we looked at these two guys. This order has Q to the B in it, potentially. This guy has a Q to the A in it, right? So we decided to get rid of that by raising it to that power. And in the denominator, GCD just gets rid of it. And I got this T, right? So let's write down our proud condition. T and what is 1. That's the order of a new guy and order of H there, right? That's Q to the A. Is that true? T doesn't have any Q in there, right? And Q to the A is relatively prime. So because of that lemma, order of what and what is a product, right? Is a T prime, T times the Q to the A. Who wants to go for it? It's a two elements whose order is relatively prime, then product has the product of order. Right, G to the QB times what? H. H is order. All right. Somebody summarize it again. What have we accomplished here? We cooked up something, has some special order, right? So what is that we are, what was our goal of number 2? Constructing an element of order greater than n. So let's write down n here and compare it. What is n? Q to the B times T. Can somebody explain why this one, Q to the A, is bigger? That inequality A is greater than bigger and T is common, right? So there. It's greater than, right? So we found one with a greater than n. So what is the next part? Contradiction. That's a contradiction. right? Contradiction to what? Maximal order is less than p minus 1. P minus 1. Okay? Big theorem and the rest of the part is relatively straightforward, although it's still interesting and mysterious, and this is the most part. It's difficult. So, ineffective proof. Let's think about that comment again. Does this help us to find that what G is? But in a way, I think this is a pretty good construction. If not, grab the other one and knock down. You see, we have G, and suppose you have G. Suppose you failed, right? This is not really the p minus 1. Then you grab H, right? And then look at the common factor and raise to that power and make it like this, and then you can go higher, right? So I think it's quite effective method, turn that to an effective method of finding the G. So let me have this discussion one more time. If you look at this item 2 here, don't think about contradiction or anything. I grabbed just an arbitrary element in here, G. It happened that it didn't reach p minus 1. How are we going to find the better one? This whole thing answers it, right? You go ahead and find element H, the G, outside that bracket G, and compare the order of these two things. And this is not going to be entirely dividing n. Otherwise, it would have been inside the G. So there is some factor out there that is not dividing the G. Then raising that H appropriately, and you can isolate that power. So that's the end of the proof. Everybody believe the proof, right? So here's some constructive method. I grabbed G, and it wasn't the whole thing. It's not contradiction or anything. It's really the process of finding the primitive root, right? If it's not the whole thing, grab something else. It's quite similar to the proof part, right? Now, you write the order of G like this, D times T1, and order of H, D times T2. And somebody explain what these T1 and T2 are and what these D are? If you have two numbers, order of two elements, there's always a greatest common divisor D and rest of the part. Does that make sense? G is greatest common divisor. So what do we know about the relationship between T1 and T2? Relatively prime, right? It's relatively prime. So if I raise that H to the power D, do you see that knocks down the D and gives you the T2? It's like kind of similar to the calculation we did, right? This is not quite right, I think. There should be a different description. This is not entirely dividing that, so there must be some prime power. I think that's a better description. So let me write that down like this, because I still don't see the T2 is relatively prime to that, right? You can't conclude. T2 is relatively prime to T1, but what about T2 and D? Are they relatively prime? I don't think so. There's the possibility. So the best way is that you're writing it like this. We have n, and there is this, let's say, A part and B part. And where B is relatively prime to n. I think that's possible. Yeah. Just leave all this part A that has a common factor with n, like prime factor. Find this B that all the prime powers that is relatively prime to. there's at least one power because of the same reasoning there. Then you can raise that to 8th power, and then it's order B. There's still, I realize there's still some clearing had to do, because if this is a prime power, and it still might have a prime power, but it's lower, just like we did A is greater than B thing, then you have to raise this one properly to eventually go to higher. So although I didn't cleanly argue it here, I'm still claiming that you can raise this G to the appropriate power S and H to the appropriate power T, such that these two have relatively prime order, and if you multiply these two, you eventually get order that is even greater than the order of that you started with the G. Therefore, you can keep going higher and higher. Okay? So becomes a constructive method. All right? It's an important theorem. That's, if you've taken elementary number theory, then understanding this proof and understanding the polynomials over finite field, how they played it inside, and that's so. Where would you say, if I look at this whole outline, where is it kicking in? What is this important property of the polynomial of a finite field is used here? One lemma, I think there's a crucial. Let me show you that. These are the collection of tools there. Which one do you think is critically using polynomials over finite field? In my opinion, I think is this lemma at most n. It's so important, right? Everything that raised to the n come inside and here because of that counting. So I think this is, if you don't have this one, everything breaks down, right?